explanation of I can't get this bolt off, we're going to explore torque and several other things that involving force and motion. So Archimedes is famous for saying, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." And that's something that we'll explore in this particular lecture. So first, our learning goals are that students will be able to demonstrate the relationship between force, torque, and distance. You'll be able to relate force to kinematic motion, what we covered in Unit 2. You'll be able to give real-world applications of torque, and that you'll be able to use this formula, which is on the formula chart. We have says balance can occur with different forces. So whenever you were doing this, the torque lab, you saw that you can actually put different masses in different locations and the lever would still remain balanced. And that was kind of interesting because you're used to it where when you have different masses or different forces that they're not going to be balanced. That's not necessarily the case with torque. We also saw that you could have equal forces or equal masses on each side and it would result in an imbalance. So we know that there's something more to torque than just force. So what we do when we look at torque is we found out that balance only occurs when the force times the distance are equal. So in this particular case, we have a force of 1 kilogram times 9.8 newtons, or excuse me, times 9.8 meters per second squared gives us 9.8 newtons. That is on the first tick mark away. We have the exact same thing on the other side, 1 times 9.8, which would be our force, 9.8, and it's 1 tick mark on the other side. So because 9.8 times 1 and 9.8 times 1 are equal, this thing remains balanced. And we saw this, we can formalize this with what we know as the torque equation. Torque, this is a Greek letter tau. It looks like a small capital T, but it's a Greek letter tau. It says torque, and its definition is the moment that causes an object to rotate. Its unit is the Newton meter, and it can be developed. You can actually be measured with a torque sensor, but we won't use anything like that. We'll calculate torque for the most part. Force we've already talked about, and then the lever arm is signified with R, although sometimes D is used since it's technically a distance. So this is the equation that relates torque, and it matches up with what we learned about in the previous investigation that says you need a force times the distance to be equal in order for torque to be valid. So torque explains why wrenches are built with long handles. So if you have two equal tools and you're trying to get a bolt off, the wrench is always easier to use because what you're doing with the screwdriver, and you can have the attachment for it, is you're twisting it and you're losing the distance from the center. The greater the distance from the center, the easier it is to cause something to rotate. So that's why wrenches have long handles. In fact, the longer the handle of the wrench, the easier it is to turn a bolt. Okay, the wrench is a lot easier to use because of the screwdriver, although a screwdriver can be very, very long, the force is exerted on a very short distance. So you're exerting the force here, and here's the turning point. That's a very small distance compared to here's the bolt, and then here's the force exerted. The greater the force, or excuse me, the greater the distance from the pivot point, the easier it is for it to move. So here's an example. It says determine the mass of an unknown to balance the lever. And so the first thing we need to do is we need to look at these things in terms of torque and in terms of left and right. If there were just masses on this side, it would cause it to rotate this way, which would be counterclockwise. If there were just masses this way, it would cause it to rotate this way, which would be clockwise. So in order to balance the lever, we have to balance the torques. So what we're going to do is we're going to go ahead and attempt to balance those torques. We're going to say we've got torques on the left, and we're going to say that we have torques on the right. And we're going to divide them up. So we're going to start with the torques on the right because there's less of them. So remember, the equation for torque is force times the lever arm. So in our particular case, we have two masses on the right. We have a 5 kilogram and a 3 kilogram. Well, the 5 kilogram and the 3 kilogram are masses. So in order to take the mass and turn it into a force, you've got to do F equals mg, or the gravitational force is equal to the mass times the acceleration due to gravity. So we do 5 times 9.8, and we do 3 times 9.8. But remember, that only gets us the force. So in order to find the torque, we have to include the distance from the center. So here's the center or our pivot point. Now normally we would look at the readings on the ruler right here, but these notches are set equidistant apart. So we can just say that this is 1 notch, this is 2 notch, and this is 3 notch. So the 5 the 5 mass is at 1 notch. Okay, and then we add, and the 3 mass is at the 3rd notch. So we can write a 3 there. So on the right side of the equation, we have 5 times 9.8 times 1 plus 3 times 9.8 times 3. So now we can switch over to the left side. And if we look at the left side, we actually have 3 masses here. So we have 3, 2, and 1. So the first thing we have is we have a mass of 3, we have a notch of 3, and we have a mass that's unknown. So we have the mass that's unknown, we have the acceleration due to gravity, and then we have a notch of 3. Then the second notch, or the second force that we have, is this due to this 2 kilograms. So now we write 2 times 9.8 times 2. And the final one we have is 1 times 9.8 times 1. Now the nice thing about this particular problem is if you look, there's common terms in each one of these. There's 9.8 in this term, this term, this term, this term. We're on this one and this one. So since there's 9.8 in all the terms, you can cancel it out easily. And that's what we did there. So what we're left with is overall, we have 3x, okay, x times 3, okay, plus 2 times 2, which is 4, plus 1 times 1, which is 1. So on the left side of the equation we have 3x plus 5. Now on the right side of the equation we have 5 times 1 and 3 times 3. So we have 5 plus 9, which is 14. So overall we now have 3x plus 5 equals 14. It's an easy one to solve. You subtract 5 from both sides, and when you do, you get 3x equals 9, x equals 3. So, in order for this thing to balance, if we put a 3 right there, it will put the lever into equilibrium. The next one is Archimedes' famous statement. It says, give me a lever long enough and a fulcrum on which to place it, and I will move the world. So we're going to test this statement out in this case. Now this is one that you're going to work out on your own, but I want to give you a couple of pointers just to look at it. The first thing is that the distance from the fulcrum of the Earth, right here, is the diameter of the Earth, because it says that it barely fits on the other side. So we want it to be just big enough for the Earth to be on the other side. We're also going to assume that all the mass is on the edge of the fulcrum. Now it's not actually there, it would actually be here, but just for the argument's sake we're going to say that all the mass is existent at the far point away from the fulcrum. Okay, so we know that this distance right here has to be 12, 7, 42000. Now, you also know that the mass of Earth is 5.98 times 10 to the 24th. Now, we know generally speaking we don't deal with mass, we deal with force. So in this case, you'd have to say torque equals force times the lever arm. Here's my lever arm. This mass has to be converted into a force. Now, just for argument's sake, what we're going to do is we're going to say that 5.98 times 10 to the 24th times 9.8 represents your force. Now I know that's not realistic because the acceleration due to gravity on the Earth does not produce a force on the Earth. It doesn't work that way. But just for argument's sake, for illustrative purposes, we're going to do that and say that that's the torque on the left side of the lever. On the right side of the lever, you've got Archimedes, and he's pushing down. So he's going to have a force of 5,000 newtons, and what you're trying to do is you're trying to solve for D. Now you should algebraically be able to manipulate this, and you should be able to figure out that the answer is 1.49 times 10 to the 23rd, to the 29th meters. Now that's the answer. To put this into perspective, Archimedes was, I guess, correct in saying that if he had a lever this long, he could lift up the world. That's true to some extent, but just to put it in perspective, That's 1.6 times 10 to the 13th light years, okay, which is a unit of distance that is usually used in astronomy. So it's over, I think it's like 16 trillion light years. The problem with that is that the entire universe itself is only something like 1.8 times 10 to the 11th light years. So Archimedes' fulcrum, his lever, would have to be 100 times larger than the actual universe. All right, we get to example A3. You should be able to figure out entirely on your own that the torque provided in this case is 100 Newton meters. So we want to be able to take what we learned in this unit with dynamics, and we want to be able to relate it to what we learned in Unit 2, which is kinematics. So we want to be able to take the force stuff and relate it to the motion stuff. And the link in this particular example would be the fact that it's acceleration. Acceleration is the link between force and motion because it's present in both equations. It's in F equals ma, and it's in 3 of the kinematics motion equations. Now it's not in one of them, but it does allow us to link it to the other 3 equations. So you are always going to want to solve for acceleration if you have a force and you're being asked about motion, or if you have motion and you're being asked about force, you need to know the acceleration. So example B1, it says a 1,000 kilogram car is initially traveling at 250 meters per second on a flat road that covers 150 meters in 6 seconds when the engine exerts 400 newtons of force on the car. Determine the coefficient of friction between the tires and the road. So I'm looking for the coefficient of friction. Now I do know that I have an equation for the coefficient of friction, and that would be Fk equals mu sub k and then mg, because it is a level surface. Okay, the problem is in trying to figure out what the frictional force is. This question is designed to make it look like you're going to have to do an if-that equation and solve for acceleration and do all that kind of stuff, but really this is pretty easy. It's telling you it's traveling at 25 meters per second initially, and then it tells you that it covers 150 meters in 6 seconds. Well, if you take 150 and divide by 6, you end up with 25 meters per second, which means that this velocity that it gave you to begin with is a constant velocity. Well, we know from what we learned in this unit that if you have a constant velocity, it's because you're in equilibrium. In other words, that the applied force is equal to the frictional force. So here, when it says 400 newtons, we now know that the force of friction is 400 newtons. So now we can say, okay, well, 400 newtons equals the coefficient of friction, which is what we're trying to solve for, times the mass, which is 1,000, times gravity, which is 9.8. Well, you take both sides and you divide it by 9,800. And the reason why you divide by 9,800 is because that's what 1,000 times 9.8 is. It cancels on the one side, and you're left with the coefficient of friction being approximately 0.041. That's the coefficient of friction. Now, just so you know, that is a unitless value. It doesn't have any units associated with it, so don't put anything there just to try and give a unit. Example B2 says, okay, a car is initially at rest and then subjected to the forces below for 150 meters. Determine the final velocity of the car. So this is one of those where it gives you a lot of information about force and is asking you a question about motion. So you know that acceleration is the link. Okay? So remember, that's going to be able to link F equals ma and then motion. So if you look right here, I've got the applied force and the frictional force, and I can find the sum of the forces. The sum of the forces in this case would be 60 newtons, because this cancels with this, and then this you subtract, and you get 60 newtons. I can also figure out the mass in this question. The mass is going to be the weight divided by 9.8. So if you take 10,000 and divide by 9.8, you actually end up with about a mass of 1,020 kilograms. Well, now I have the sum of the forces and I have the mass. I can solve for the acceleration. Once I have the acceleration, I plug it into my kinematics variables, which are initial velocity, displacement, and then now I have acceleration once you calculate it, and you can solve for the final velocity. You should be able to calculate the final velocity of this car is 4.2 meters per second, and you should be able to reproduce that on any sort of quiz. Example B3 says you have a 500 kilogram box being pushed on a horizontal surface with a net force of 100 newtons to the right. How far will the box move if it was initially moving at 2 meters per second to the right? So we're looking for how far, and since we're looking for how far, we know that that is a kinematics problem. But once again, we're given information with force. So we know that acceleration is our link. So the first thing we want to do is we want to solve for the acceleration. We are given the net force, which is our sum of the forces. We are given the mass, which is 500, and we should be able to solve for the acceleration at that point. Take the acceleration, plug it into if that, and you should be able to say that the box will travel 25 meters in that 10 seconds.